Good morning. How are you guys doing? I hope you had a good J term and I hope you're ready to start second semester here. I wanted to start off talking about lab reports. I went ahead and made some changes to this handout, which I will post to Canvas when I'm done here, maybe in an hour or two. It's going to look like this, and I wanted to go over a couple points with you. I'd love to see our lab report step it up a notch this semester, okay? So a couple points I'm going to make is number one, font size, okay? It's all on here. The font of your whole lab report should not be bigger than 12. In fact, 11 is probably fine. Some of you are turning in lab reports in huge font, and it's very unprofessional looking. So the headings can be a size 12 or 14 font. The rest of your text needs to be a size 12 or 11. Also, I want to point out this lab report number here that goes at the top of each lab report. That's not the number of labs we've done this semester, like number 1, number 2. It's the actual number in your textbook, which is usually the module number and then a period and then the number of lab that it is for that module. So for example, the lab I'm having you do at home today is experiment 9.1. So that's what that should say up here, is lab report 9.1. The next thing I want to say is in the data section of your lab report, I want you to put a chart or data table every time. I can't think of an example where that's not going to be appropriate. So for today's lab, you're going to put the eggs on top of a ramp and have them roll down together. Then you're going to have one sitting at the bottom, and then you're going to have one time where they're facing each other, going down 2 ramps and smashing each other. So your data table could look like this. I want it to say, up here would be the titles, and it might say trial 1, okay? And then you put here, I guess trial 1 might be over here. Sorry. And so you're going to say, this is when both eggs went down the ramp together. This is trial 2. This is where, one egg went down the ramp, the other egg sat at the bottom. This is trial 3. And you can put, they came down 2 ramps facing each other. As I'm thinking about this, these aren't really trials. A trial would be like doing the same thing several times to see if you get the same answer. So maybe this is like case number 1, case number 2, case number 3. Sorry, I didn't have that figured out before this video. Okay, then you're going to put your observations. So what happened in each of these times, okay? So whatever your data is for whatever kind of lab it is, we're always comparing. This is what happened when I did this. This is what happened when I did that. So I need that to be reflected in a table. It's just an easy way to organize your data. I added a section on here called possible errors, and that's, if your ramp was too wide and so your egg went wild and it didn't do what you thought it was going to do, okay? You don't always need an error section, but if you feel that something went wrong in your experiment, that's where you can talk about it. Then the last thing is your conclusion. The conclusion needs to bring it home. Yes, it needs to talk about your hypothesis. Was your hypothesis correct or not? But it needs to connect what you did in the lab to the concepts we're studying in class or in the textbook. So the book actually, the text for like a half a page or so after the lab every time kind of tells you, does that for you. So basically you need to read that and summarize it in your own words, okay? This is what I learned in the lab. This is, this happened because of this scientific principle, or this is confirming this scientific principle. You need to not just have like one sentence. I'd say your conclusion needs to have a minimum of 4 to 5 sentences where you are explaining like, why did we do this lab? What did this lab have to do with this module? Okay, so I want to see that reflected. You're going to write a lab report based on the lab you're doing at home today. And so I hope to see these changes in what you turn into me next week. Just a reminder that I need your lab reports printed out and turned in person to me on Mondays. And if you do not have it printed out, I will have to count it as late, okay? Because I like to write notes on your lab reports, and I don't know how to do that electronically. So it needs to be printed out. If you're doing the lab at home like today, please include a picture of yourself performing the lab or of the result of your lab, something, and include that in the lab report. Okay, so we are done talking about lab reports, and now we're going to move on to the content. So, second semester of this course is physics-based. So, the textbook mentions the fact that physics is a fundamental science. And I just wanted to explain that a little bit. I think there's a few reasons that physics is considered a fundamental science. First of all, the study of the atom and what's inside the atom and even what's inside protons and neutrons and the forces that hold the nucleus together and the behavior of the electrons around it, all of that is physics. And of course, that's the most basic building block. Chemistry builds on top of that and says, okay, let's put some atoms together and make molecules. And what happens when this molecule meets this one and it reacts and it makes a new molecule? Okay, so that's chemistry. Then biology goes a step further into life. And now how are these chemicals and processes affecting the cell and living things? So just from a size perspective, the very smallest building block for science is based on the physics of the atom. But also the book talks about physics being the study of motion and kind of the reason behind a lot of things. And it has a quote from Thomas Aquinas that I thought was really neat that you'll read in your reading. He says, when the universe began, something had to be there to start all the motion we see today. Aquinas says that God is this original mover, and I think that's really neat. So anyway, physics is the study of motion, how things relate to each other, the forces that help them interact, as well as waves of sound and light, and the forces between them, the motion, the way they interact. So we're going to have a lot of fun. This is my area that I enjoy a lot and that I know more about than weather and the troposphere and all of that. So I'm excited for this semester. So let's go ahead and dive in. If you don't already have a pen out with your notebook, with some blank paper that you can write on, then please go ahead and get that out. So what this module is about is motion. And here's another thing about physics, is that it's all about numbers. It's about quantifying them. And that is one of my favorite things about physics, is that it can observe the natural world, okay, throw a rock and observe it, and put it into a mathematical equation. I mean, how many things in life can you do that with? You know, like let's say you tracked what you ate for dinner every night. You could make a data table, you could make a chart, you could look at it, but could you make it into a mathematical equation to figure out what you're going to have for dinner tonight? I don't think so, you know. So most things in our world, and even in chemistry and even in biology, you can't necessarily put a number to. But in physics, what totally blows my mind and amazes me is that God set up the rules of the universe so that when we observe them and count them, they fit together so amazingly that they work in equations. It's totally mind-blowing that they're so consistent and reliable that it even works in an algebraic equation. Advanced physics uses extremely advanced math. Just when I studied physics in college, I had to take math, I think 2 levels past Calc 3, and there was still math in physics that I couldn't comprehend. So theoretical physicists who are out there trying to come up with a theory of the universe and that kind of a thing use math in multiple dimensions, like up to 11 dimensions, 12 dimensions, and the math gets crazy. So in this class, this semester, we're not going to go beyond a basic equation, which I think you're all familiar with, whatever level of math that you're at. But I want us to not dread the math, but to see like, this is amazing that we can make these observations and put them into an equation and get real information after that. It's really spectacular in my opinion. Okay, so we're going to be using math. We're going to be using math every module through the end of the semester, so that's a lot different. Also, think about weather, think about the troposphere, think about learning about the layers of the earth. A lot of that is categorical, is memorizing. And so physics is really different, that it has this mathematical dimension to it. All right, let's talk about motion. How do you know that something is moving? Okay, I'm going to take this marker. Okay, was that marker moving? Yes. How did you know? Probably because you saw it in this place, and then you saw it in this place, and to change positions, you knew it had to move. Okay? So the basic idea of motion is that there has been a change in position. Okay, position is just the location of something. I'm sorry I wrote that up there in advance. I hope that's not been distracting you this whole time, this speed equation. So if there's been a change in position, there's been motion. Because we can't just snap our fingers and have something reappear in a different place. It had to move to get there, okay? So, so we can think about anything. We move things all the time, don't we? We pick up a book in one room and set it down on a table in another room. So you could track the change in position of that book and figure out how far it went, right? Well, if we want to track how quickly something moves, see, so I've got this like this. Now I'll do it a different speed. Wow, that was so fast you could hardly see it. I'll do it another speed. All of those times of me moving the marker, it had the same change in position, right? Started on one side of the screen, moved to the other side of the screen. What was different about them? Well, the speed was different. How do you know that? How does your brain track speed? How did you know that one trial I moved the marker faster and another trial I moved it more slowly? Well, let's think about that. It has to do with time. So if I started a stopwatch here and let it go until I moved over here, a certain amount of time elapsed. I think that took 3 or 4 seconds, okay? But now what if I started my stopwatch and went like this and ended it? All right, that was probably less than a second. So what we're doing there is we're changing the amount of time it took me to make that change in position. So speed is going to be, equal my change in position, which in physics we would write this as a delta. That means a change in something. You could have a change in time. You could have a change in temperature. You could have a change in position. Position, we use the letter X. So change in position is delta X, or we use a different word for change in position in daily life, and that word is distance, okay? What's the distance the book traveled, or the marker traveled, or the car on a road trip? Okay, we use the word distance, and what we're really saying is it had a change in position. So we're going to say that speed is distance divided by the amount of time. And I'm going to put delta t, okay, or I'll write out time. Your textbook seems to not want to use symbols for these ideas. It wants to use the words written out. But I think you've all had enough algebra that hopefully that won't scare you away. So we might say speed equals distance divided by time. Okay, d divided by t. So I'm going to do an example from the book for you that we can kind of work on together to try to get you this idea. So this question, example 9.1 on page 207 of your book, says a car travels 78 miles down the highway. It takes the car 1.2 hours to travel that far. At what speed is the car traveling? Now, it might seem just really easy to plug it in right now, but I want you to have good habits of how to solve problems, because physics, and as you take physics later in high school, it's all about problem solving. Like this kind of problem is typical. You'll get a lot of these and they get more and more complicated. So I want you to just start up good habits right now of how to tackle a problem like this. So step number 1 is your equation. Figure out what equation you're going to need based on the things they give you and the things that they want you to figure out. Maybe this other step here, second step, should have come first. We'll practice this again. Another thing is, let's write down what the problem told you. All right, and let's write it down using these symbols. So did the problem tell me my speed? No, actually it asks for speed. It says, at what speed am I traveling? So I'm going to write speed equals question mark because that's the thing I'm looking for. All right, did my problem tell me distance? Yes, it did. A car travels 78 miles down the expressway. So I'm going to write D equals 78 miles. Okay. What else did my problem tell me? It takes the car 1.2 hours to travel that far. What is that? 1.2 hours. Is that a speed? Is that a distance? Or is that time? Okay, you're going to have to figure that on your own because the problem doesn't say T equals 1.2 hours. So you have to figure out, okay, the problem said 1.2 hours. I think that's a time. So I'm going to say T equals 1.2 hours. All right. Now I've got the things I know, the thing I don't know, and I'm going to plug them into my equation. Okay. Step 3 is called plug and chug. Okay. So speed equals, now instead of D, I'm going to write what D equals, 78 miles. And instead of T, I'm going to write what T equals, 1.2 hours. Okay, and that equals 65. And then what are my units? So I had miles up here, I had hours here. There's nothing to cancel out. If you can't cancel units, you have to keep them. And you have to keep them in the mathematical structure that they're in. You can't change this into miles times hours or miles minus hours. You have to keep it whatever the math was of those units. So it's division here, isn't it? So it's going to be miles over hours, which is miles per hour. Now in daily life, right, we write that MPH, 65 MPH, miles per hour. So, but in like a physics kind of a concept, you know, to keep it consistent, we would do miles per hour written like that as a fraction. Okay, so a lot of these examples, they might give you the speed and the distance, and you have to figure out the time. They might give you the speed and the time, and you have to figure out the distance. So figure out what things they gave you and what thing they want from you. And then you might have to use algebra to rearrange your equation in order to get your answer. Okay. Let me see. The next thing you're going to read about is called vector versus scalar. Okay. So let me erase this. And that's what your lab is about, vector and scalar quantities. So the idea is this. If I have a car moving this direction, okay, and there's a van moving this direction, how can I compare their speeds and really like compare how much distance is between them and that kind of a thing? If I said that the car is going 60 miles an hour and the van is going 70 miles an hour, okay, sorry, I'm going to go ahead and use MPH since that's just easy. How can I compare these speeds? Because they're going in different directions. And so what it turns out is that when a quantity like a speed or a change in direction doesn't have any direction assigned to it, if all you know is 65 miles an hour or 60 miles an hour and you don't know what direction, it is called a scalar quantity. Okay, so Hang on just a second. I will be right back. I'm back. So it's scalar if it has no direction assigned to it. But can you see how it would be helpful to have a mathematical, direction matters, okay? So I need to know, are my van and my car getting farther apart? Are they getting closer together? How can I figure that out if I only know their speeds? So what we do in physics is we turn it into a directional thing. And so often we might say, this way I'm going to call positive and this way I'm going to call negative. So I might say that the van is going negative 70 miles an hour and that the car is going positive 60 miles an hour. And then it is called a vector quantity, because vector means there is a speed given and a direction given, okay? Or a quantity and a direction. And so you see how important this might be. If you think about airplanes in the air and where they're going, it wouldn't be enough to know the position and speed of the airplanes. You'd need to know what direction they're going in, right? So that you could make sure they don't crash into each other. So for air traffic controllers, I'm not sure what units they use. Plus and minus wouldn't work, would it? Because they've got 360 degrees to cover. So they probably use, northwest, 15 degrees northwest, something like that. That would indicate the exact direction that the plane is going. So those are vector quantities. And this is really useful in comparing speeds. So if you wanted to compare the speeds of these in a scalar way, which vehicle is traveling faster? Well, the van is going 10 miles an hour faster. How did you know that? You said 70 minus 60 is 10, okay? Well, that's a scalar idea, just in terms of thinking about the car, how fast they're going to get to their destinations. It is going 10 miles an hour faster. But if you want to compare them and kind of the speed that exists between them that they are separating by, how quickly are those two vehicles moving apart from each other, then you would subtract them in this way. You would say 60 miles per hour minus a negative 70 miles per hour. Okay, and what happens when we have minus minus? Of course, they become positive. And so we have the speed between them is 130 miles per hour. That's how quickly they are moving apart from each other. So I hope that makes sense, and that's what your lab is supposed to be showing us, as how important it is to know the direction. So then there's an example in here. Two cars are traveling down a road. The first car is traveling north at 55 miles an hour, and there's another car traveling north at 45 miles an hour. Okay, so comparing those speeds. Well, they're both going the same direction, so we're just going to subtract them to figure out the difference in their speed. But then it gives you an example of them moving in opposite directions, very similar to this. I think he prefers the math in a different way. Instead of saying positive and negative, he just wants you to outright add them when they're going a different direction. Okay, it's the same however you want to think about it. I prefer thinking that one direction is positive, the other's negative, and going from there. All right, so that's what velocity is all about. And relative speed. This idea is relative speed, okay? 60 miles an hour is how fast the car is going compared to the road, compared to everything that's stationary. But 130 miles an hour is the speed that they're going relative to each other, okay? If you tried to compare how quickly their distance is gaining between them, that would be relative speed. All right, now your book just jumps right into acceleration. So usually I would spend a lot more time on these concepts, but this is kind of just an overview. So we're just going to jump through these ideas. So acceleration, I'll change colors here. Acceleration is the idea of a change in velocity. So while we can think about a car going 60 miles an hour, we can't, go 60 miles an hour forever. We have to speed up to get to that speed. We have to slow down to stop. And so for those times, my velocity is changing. And whenever we have a change in velocity, it's called acceleration. So change in velocity. Oh, I didn't define velocity, did I? Is acceleration. Okay, let me go back. Velocity is simply the vector word for speed. So in daily life, you might use those two words interchangeably. Like, oh, the velocity of that Lamborghini was amazing. And really you just mean speed. But in science, velocity is speed and direction. So like what we talked about, vector and scalar. So velocity is a vector word for speed. So speed means you just know how fast it's going. Velocity means you know how fast and in what direction it's going. Okay, so it's a very similar word. It just is a little bit more specific in having direction involved. All right, so any kind of change in speed or change in velocity is acceleration. Okay, so very similar to our equation for speed is our equation for acceleration. We're going to say that acceleration is A, and remember our symbol for change in is delta, change in velocity over a change in time. Okay? So the book writes this differently. It calls this final velocity minus initial velocity. And I think it just calls that time. Okay, but obviously it's a change in time. It's not one snapshot in time. So don't be afraid that I'm using symbols and the book writes the words out completely. It's the same thing. So to find a change in velocity, we need to find, well, what was the velocity at the end and what was the velocity at the beginning? And if we can subtract those, we'll find out the change. So let's say the car was traveling at 5 miles an hour when it entered the expressway ramp, and then over the course of 20 seconds it sped up to 65 miles an hour. So what was the change in velocity? Well, we would say that to keep things positive, we write the final velocity first. So that car had a velocity of 65 miles per hour at the end, and at the beginning it had a velocity of 5 miles per hour. So 65 minus 5 is 60. Our change in velocity was 60 miles an hour. Then I said it took the car 20 seconds to do that. Okay, so let's put 20 seconds. Now, we might be tempted to say, okay, 60 divided by 20, that's 4, that's 3. So, my acceleration was 3. Well, we would be completely forgetting about units. So, we've got to keep our equations in the same units. So remember what MPH is miles per hour. So if we suddenly divide by seconds, we've got our time in 2 different sets of units. And so our answer can't get any more specific than 60 miles an hour divided by 20 seconds because our units don't communicate with each other. So let's figure this out. If my acceleration is 60 miles per hour over 20 seconds, I need to get my time in the same units. So let's change our hours to seconds up there. Now, I think we did this a little bit first semester, but you're going to need a little practice here. So 60 miles per hour, I'm going to do it like this. Miles per hour. We're going to have to multiply by something to get me to seconds, okay? So how many minutes are in an hour? We have to go through minutes as well. We can't skip it directly from hours to seconds unless we know how many seconds are in an hour off the top of our head. So there are 60 seconds in 60 minutes in 1 hour, aren't there? Oh, but I want it the other way. All right, if you make this mistake like me, if I multiply hour by hour, I'm not helping myself. What I'm trying to do is cancel out units, okay? So I got to flip that around. There's 1 hour and 60 minutes. All right, I'm almost there. How many seconds are in a minute? There's 60. So I'm going to put in 1 minute, there are 60 seconds. All right, now how can I cancel some stuff out? This hour cancels with this. These minutes cancel with this. So now I'm going to be left with seconds on the bottom instead of with hours on the bottom. So this is going to work. I still have my 60 up here. 60 times 1 times 1. And my units, that canceled and that canceled. So my units on top are still miles. 60 miles. Then what do I have here on the bottom? Well, this was 1 hour times 60 times 60. What's 60 times 60? Well, 36 with 2 zeros. Okay, and my units on the bottom are seconds because my hours got canceled, my minutes got canceled, so I just have seconds. Okay, so my real speed that I can use in this equation is 60 miles divided by 3,600 seconds. All right, so let me plug that in, and to my calculator, 60 divided by 3,600 equals 0.017 miles per second. See if that makes sense. So a second is a really small unit of time, okay? So in that really small unit of time, would it make sense that I'm going 0.017, a really small distance? Yes, it would. All right, now instead of 60 miles an hour, I'm going to put 0.017 miles per second. Boom. All right. Now that's something I can divide. divided by 20 is 0.00085. And what are my units? Well, I'd like to think that these seconds could cancel, but they don't. It's miles divided by seconds again. So that is miles divided by seconds squared. Okay? So for acceleration, my units are always going to be a distance unit divided by seconds squared. Okay, that's just the way acceleration works out, since it's a velocity divided by a time, and velocity already has some seconds in there, that it's always going to be seconds squared. So the acceleration of my car entering the expressway is 0.00085 miles per second squared. Now we use miles since we started off in miles per hour. In a lot of physics, we use meters per second or meters per second squared, since that is the SI unit for distance. Okay, so let's see, there are some examples in here about falling, okay, because free fall is a great example of acceleration. If I could stand on this chair and drop this ball, okay, I would find that at the top it's not moving. I'm just holding it. And then as it falls, it's going to get faster and faster and faster. So isn't that an example of acceleration? If I could hold up a radar gun and figure out how fast it's going, maybe a half a second after I let it go, and how fast it's going before it hits the ground, the speed is different, right? It's going to go more slowly up right when I release it. It's going to be going faster before it hits the ground. Have you ever stood on a bridge over a stream and dropped some sticks in, for example? The sticks are moving pretty slowly when you release them from your hand, but before they hit the water, they're going a lot faster. So that's a change in speed over time. So they are accelerating. So when something falls, it's in a state of acceleration. This video has gotten really long, so I'm going to wrap it up here and just say that these problems all work a lot like this. Go through the examples and just remember that it's a change in velocity divided by the change in time to get your acceleration. Let me know. Send me a message if you have a question about any of your homework or your lab, and I will see you next week. Bye-bye.